Okay, so what we are going to look at is the acceleration and potential, of course, gravitational potential, that is what we are talking about, of a distribution of mass, okay? Not a point mass anymore, distribution of mass. So for that, let us consider a body, which has an arbitrary shape, okay? A 3D body with an arbitrary shape. It can be anything, okay? And to do our job, okay, and then of course we can think that this particular body is made up of several small point masses. Let us call them as maybe m1, m2, so on and so forth, mn. Okay, it's the accumulation of such masses. Okay, and then suppose at a point P, I wish to understand what would be the acceleration and what would be the gravitational potential for this particular body. Okay, and let us say from M1 it is at a distance. This point P is at a distance of R1. From M2 it is at a distance of R2. From M3 it is at a distance at R3. Okay. And to do our job, in a bit more methodical way, we can actually also introduce a Cartesian coordinate system here. Okay, so suppose this is X, Y, and Z. Okay, so how do I how would I write the expression for AG then? AG should be essentially the accumulation of all the gravitational acceleration of all the point masses. So that is like capital G M1 R1 square R minus G M2 R2 square R minus G M3 R3 square R, and so on and so forth. Okay. Similarly, I can write down for UG, that is the gravitational potential. You remember we will not have a R square. Rest of it will be the same. So minus G M1 R1 G, and so on and so forth. Now, there is a problem in such approach, and the approach is the problem in this approach is that discretization of mass is not a feasible idea. Okay, what we are trying to do here is that we are discretizing each masses, right? So that is not a feasible idea because mass is a continuous body. Yeah, you cannot simply discretize mass like I have done it here. Okay, and it's a continuous body. Okay, but volume can be distributed. Okay, so what we can think of a small volume delta V, okay, or dV. We can think of a small volume dV, and then we can find out what would be the gravitational acceleration and gravitational potential due to this particular volume delta V on this point P, considering uniform density. Okay, considering uniform density, and then we can essentially integrate for the whole volume. Okay, so if we do that, we can write down UG is equals to minus G, of course, and then we are integrating against X, Y, and Z, of course, right? So rho X, Y, Z r x y z dx dy dz. This is nothing but integrating the volume delta v. Okay, so rho into dx dy dz is nothing but delta v. So this expression is essentially accounts for delta v. So if we think that the total mass is of the mass of the earth, so if I say the mass of the earth is capital E, then we can write down this expression as minus G capital E by R. Okay. Now, if we think of that this is the earth, and of course, this is the radius of the earth, and let us designate radius of the R as capital R, and we want to consider the gravitational potential and acceleration on the surface of the earth. Okay, then we can replace small r with capital R. Okay, we can replace small r with capital R. Okay? And similarly, AG will then be small GE by R square in a vector. All right. So this is what we can do. Now, tell me, can you do a quick calculation? So we have got this equation that AG is equals to GE by R square. Okay. If I give you the value of AG being 9.8 meter per second square, something, like a standard value, and the radius of the earth is around 6371 kilometers. Can you calculate the mass of the earth? Quickly do it for me, please. Okay, you know the value of G, which is 6.675 into 10 to the power minus 11. Yeah, 6.6674 you can take into 10 to the power minus 11 meter cube kg per second square. Okay, meter cube per kg per second square. So I can write down G for you as well. 6.674 into 10 to the power minus 11 meter cube kg second square. Okay, can you calculate E quickly for me? And express it in terms of kg. Okay. Now tell me, if you write down, I have to switch my screen. Yeah, done. Donald, tell me, do you have a question? Okay, you have got the answer. 5 point. Okay, can you express your, equation? Sorry, your answer, like one digit after decimal, like 5.9 into 10 to the power how much? So 5.96 into 10 to the power 24 kg, something like that, isn't it? say 5.97. Is it 10 to the power 24? Can you check? Is that right? Yeah. Okay. If you please don't write answer on the chat box. Can you please speak out so that I don't have to switch the screen every time. Okay. All right. Now, what would be the volume of the Earth then? Volume. What would be the volume? So if I consider the Earth to be a sphere, 4 third pi r cube, right? So just tell me what would be the volume of the Earth. Let's express that in terms of meter cube. Come on, guys! I told you not to write there. You can speak up.
1.08 into 10 power 21.
The problem is I have to again switch the screen to look for it, na? So I lose that. Tell me the answer, Danal. Tell me. Speak up once more. Hello. What happened? Hello, can you hear me? Hello? Yeah, just tell me your answer.
So it's 1082.65 meter cube.
1000
82
10.65
1082.65 meter cube.
meter cube.
Yes, sir.
Okay, now can you calculate the density then? What would be the density of the Earth in kg per meter cube, and then express it in gram per cc? Okay, express your express the density of the Earth in gram per cc. What would it be?
Sir, it's 5.46 into 10 to the power 3 kg per meter cube.
So in gram per cc?
Sir, it would be 5.46 gram per centimeter cube.
5.46 gram per cc. Okay. So let's just write down, just for being, bit more, just round it off, 5.5 gram per cc. Okay. You agree with me? Now, what is the density of the, you have read this, what is the density of the continental crust? Huh? What have you read?
2.8.
2.78 gram per cc. Okay. What is the same for the oceanic crust?
3.2.
3.2 gram per cc. Okay. Now you have just calculated it is 5.5 gram per cc, but we have said that the the oceanic crust, of course, you can see from the mean density, the oceanic crust density and the continental crust density is way lower. Now, why is that? Can you guess? Can you tell me why is that? Why this difference is? It's almost double, right? So what does that mean? What does that indicate?
Sir, that would mean that the other constituents or maybe the inner layers are much more denser.
Absolutely. They are heavier, okay? So the core and the mantle has to be denser, okay? Okay. Are denser than crust, okay? That is one point. And the second thing, of course, that the mass or the density is not equally distributed. You agree with me? The mass or the density are not equal, they are not equally distributed throughout the earth. Okay. So now that brings to one of the important concept, what we call as equipotential surface. Okay. So equipotential surface is the imaginary surface on which all the, this particular case, we are talking about gravitational potential. All the points have the same potential. So that's right. So say, for example, if this is the Earth, okay, suppose we go at a distance, whatever it is, and we think of an imaginary shell surrounding the Earth. Okay, at every point of this would be called an equipotential surface if at every point of this UG is the same. Okay, this would be called an equipotential surface. Okay, now tell me, suppose this is R1, this is R2, this is R3, this is R4. How many of you think R1 will be equal to R2, will be equal to R3, will be equal to R4? You know what I want to say? Suppose if I think that the Earth is a sphere, or let's not think that the Earth is a sphere, the shape of the Earth, that whatever it is, we will see how it is. You have some idea how does it look. What do you think? Will the equipotential surface be equally distant from every point of this, every point on the surface of the Earth? Will it be equally distant?
So if the Earth would have been a perfect sphere, then it would be.
Very good. If not, then they will
Then
not
it
be.
will not be.
That will not be, because it is heavily dependent on the distribution of the mass, right? So if the mass is not equally distributed along the at different parts of the Earth, it will be differently distributed. Okay, so you already know, for example, if you think of the Mid-Oceanic Ridge, this is how the Mid-Oceanic Ridge looks like, right? So here the oceanic crust is really, really thin. Okay, and then your mantle essentially comes up, right? And in another case, of course, you can have an oceanic crust of a normal thickness. Okay, and we have just said, suppose this is row 1, this is row 2, and this is row 1, this is row 2. The effective density in this particular case, suppose, is row 3, and the effective density in this case is row 4. Just by the logic that we have talked about, the mantle and the core has different density than the crust, the row 3 and row 4 will be different. You get my point? And that is also because the mass is not equally distributed, we do see that the equipotential surface is not, at the same height from all points of the Earth. Okay, so this is one thing, and the second thing that you talked about, that the Earth is not a perfect sphere, and we will discuss about this, and this particular phenomena, that the equipotential surface is not everywhere the same. We will use that for our geophysical prospecting. Okay, this is what we will use as a guiding principle for our geophysical prospecting, in this particular case, gravitational prospecting. Okay, how we will see later on gravitational prospecting. Okay. This non-equal distribution of mass. Is it clear? Any question do you have?
Sir,
Yeah.
so it doesn't depend on sphere, the shape of the Earth, right?
It does depend on the shape of the Earth as well.
So
fundamentally, it is dependent on the mass distribution. So mass distribution can be different the way I have explained, because of the thickness of the crust. If the crust is not equally thick everywhere, then the mantle in some places comes up, in some places goes down, right? So that will change my effective density. That is one thing, and of course the shape of the Earth. Sometimes the surface of the Earth is kind of flattened from the mean surface. We will see that, and sometimes it is kind of going up from the mean surface. Okay, let us say the mean sea level is that mean surface. Okay, and we will see some places it is up, some places it is down. Okay, and that doesn't make it a perfect sphere, and the not being it a perfect sphere also contributes to the unequal distribution of density. Okay, so both of them does.
okay, sir.
Okay, anything else? Is it clear for you what I just said? Did you understand my explanation or
Yes,
not?
sir.
Okay. Anything else? All right. If not, then let's move ahead. Now we are going to bring in another concept. And this concept is also known to you. That is what we call as centripetal acceleration. Centripetal and centrifugal acceleration. Let us just look at centripetal acceleration first. Okay. Let us say this is the sun, And let us, just for the sake of simplicity, let us think of an circular orbit. Let us say one planet which is moving, okay, along this orbit. Suppose at a particular point it is making an angle theta, okay, from this coordinate system that I have just defined. Okay. And the linear velocity of this particular planet is v, which I can resolve into two components. Suppose this is y, this is x, as vy and vx. Okay. And the angular velocity is omega. Okay. So the theta will be is equals to omega t if the time taken, from here to here is actually t. So the time taken from here for the particular planet to move from this position to this is t, then theta is equals to omega t. Okay, we also know. Let us talk about some very basic equations. You know about them. Okay, so v is equals to r omega. You know that. Okay, where this is r, of course, right? V and Vx is equals to minus V sine omega t, and we can write down V is equals to r omega, so minus r omega sine omega t. Similarly, we can write down Vy is equals to V cos omega t. Okay, and this is Rw cos omega t. Okay, and let us, so if this is the case, the centripetal acceleration, if I just try to draw how the centripetal acceleration would look like in the same picture. It is directed inward. Suppose the centripetal acceleration is a, okay, and it has two components, ax and ay. Okay. Now what we can do, what we will do, how would I get the acceleration from velocity? What we need to do is simply we have to differentiate that, right? So we can write down ax, okay, is equals to, this is differentiating Vx with t will be equals to minus omega V cos omega t. And if I simplify that we can write down is equals to r omega square cos omega t. And similarly, ay can be written as minus omega V sine omega t, or r omega square sine omega t. So a is equals to root over of ax square plus ay square. Okay, or a can be written then is equals to omega square r. Okay, so the centripetal acceleration is actually A is equals to omega square r. This can be further written down. How do I get that? Is r square omega to the power 4 sine square omega t plus cos square omega t, right? This is just by squaring x and ay, and sine square omega t plus cos square omega t is 1. So this is root over r square omega to the power 4. That takes omega square r. So A is equals to omega square r. Omega square r. You know about this one. Now, we have talked about centripetal acceleration. Similarly, we know about centrifugal acceleration. So centrifugal acceleration is oppositely directed from centripetal acceleration. Okay, and let us say we can write down this is centrifugal acceleration. Let us call it as AC, and that is also omega square r. Okay? Or we can write down that as from linear velocity v square by r. Okay. Now let us say UC is my centrifugal potential. Okay. So AC, the centrifugal acceleration, can be written as delta UC delta X. Okay, with the same logic, for GM by R square and UG, it's the same logic. It's the differentiation of the centrifugal potential. Okay, so we can write down that is equals to omega square X, right? So then UC will be half omega square X square. Okay, and now let us say we have just drawn this. So this is theta. Okay, and this is, suppose, say for example, if I now consider that this is the Earth, this is the Earth, and we are trying to think of, now the Earth is also rotating, around its own axis, right? So now let us say this is theta. So what does then theta mean, in terms of our common language? If this is the Earth, okay, and I take a point P, and from the center of the Earth, I'm kind of joining it. So this is the equatorial plane. What does this theta mean? Do you know?
It's latitude.
Is it latitude? Yeah. So this is essentially my latitude. So what is the common term of putting latitude? The common term of putting latitude is actually your lambda. Let us just say this is lambda, okay? Sorry, what is that? Sometimes this whiteboard starts acting really funny, and I get confused. Now it should be in the pen mode. Why is this in the eraser mode? I don't understand. I have clicked on the pen, you see? It's still in the eraser mode. Why? Come on, man. Yes. Okay. So let us say this is lambda, which is latitude. Okay. Let us say this is my AC, right? This is my centrifugal acceleration. This is x. Okay. And let us say this is theta. Okay. So then theta here will be called as co-latitude, which is nothing but 90 degree minus lambda. Okay. So if we do that, see, I will be again in trouble. No, I hope not. So I can write down and if this is r, right? This is r. Okay. This is x. So I can write down this is equals to minus half omega square r square cos square lambda. Okay. Or we can write down half omega square r square sine square theta. Okay. So this is how the centrifugal potential is defined with respect to the latitude. Okay. Remember this equation. This we will use it for our purposes later on. Right. Now, let's draw that, sorry, let's draw that figure once more. We are again drawing the Earth, okay? And this is any point at the surface of the Earth, okay? And the Earth is rotating along its own axis, okay? So this is theta, co-latitude. This is lambda, which is my latitude. This is r, and this distance is x. And this is AC, which is my centrifugal acceleration. Okay. Now, let us say that the distance between a planet at any point in time, the distance between a planet and the sun is rp. Okay. So what can be said that at that particular point the the centripetal acceleration and the gravitational acceleration has to be the same. Okay, so the centripetal acceleration and the gravitational acceleration has to be the same. So if we say that the mass of the sun is S, we can write down what would be the expression for the gravitational acceleration? Gs by Rp square. Yeah. And that will be equals to my omega square Rp. Okay. Now, if I do some here and there, what I can find out, I can write down Rp square. Now, this can be expressed as omega is equals to 2 pi by Tp. Okay. Tp being the time period and 2 pi being the periphery. Okay. By Rp. Okay. So omega square, omega is expressed by 2 pi by Tp. Okay. So from here, what I can write down, Rp cube by Tp square is equals to Gs by 4 pi square. Now you can see G is a constant. The mass of the sun is constant. It's not going to change. And 4 pi square is of course a constant. So Rp cube is directly proportional to Tp square. Now what have we derived just now? Rp cube is equals to is directly proportional to Tp square. Which is this law?
Kepler's law.
Kepler's law.
We have, so from that we can, this is the Kepler's third law. Okay. Now let us just consider moon from the earth with the same logic. Okay. So now suppose here is my earth, and then at a distance RL, yeah, L means lunar, okay. So here is my moon, okay. So the mass of the earth is E. So Ge by RL square, that will be equals to omega square L RL. Okay, we can simplify this equation a little bit. Ge by RL square. Just work with me some here as well, okay? Sometimes I might make a mistake while I write these equations. Square. Just point out, huh? If I am making a mistake. RL by R. Okay. This is something I can write down, isn't it? Should not be a problem. Now, from here I can say then now this expression is the expression of Ag, right? So Ag will be equals to omega square L R by small rl by R cube. Now this is what we know, RL by R, R being capital R being the radius of the earth, okay, is around 60. Okay, the T for the moon is around 27.3 days. Okay, and RL Now, if I consider the if we consider that R is around 5400 kilometer, that is what people used to know during the time of Newton. Okay, this is the value of R that they have calculated. Okay, you can calculate the value of Ag is around 8.4 centimeter per second square. So previously, using this particular equation, actually, Newton calculated the gravitational potential, but he did not have a very good value of the R, capital R, okay, which is the radius of the Earth. Nowadays, we know that the radius of the Earth is around 6371 kilometers. So now, if I replace that value with 671 kilometers, I will find the value of Ag using the same equation, is around 9.81 meter per second square. Okay, so just by equating your gravitational acceleration with the centripetal acceleration, you can also calculate the gravitational acceleration. Okay, because and this there are and using some astronomical data which people used to know from the very beginning. Okay, I think these are all very much known to you. So I just wanted to recap that. But tomorrow, not tomorrow, tomorrow is a holiday. So on Monday onwards, so there will not be any pre-recorded lecture tomorrow because tomorrow is a holiday. We will start looking at gravitational potential into a bit more details. We are going to talk about Legendre's polynomial and Laplace's equation, and then see how we can apply that to define gravitational potential better. And from there, we will slowly get into the complications around the equipotential surfaces. Okay, so if you have any question, you can ask. Have you got the email that you have to register yourself with this, what is the name, this examination thing?
Yes, sir.
Yes, sir.
Yeah. Yeah. What is that? Code Tantra. Yeah. Right. So it's going to be something like the examiner, right? Which we had in the campus. Do
It's
you know?
more complicated than it.
It's complicated.
Yes, sir. Because it has a lots of rules and regulations to follow.
Oh
Sir,
my
and
God.
there are a lot of problems with the
And sir, the
platform also.
moment
We were looking at, my friends are looking at it, and it has like 1.9 rating online and
Oh
all.
my God.
so the problem is that if we are having 4 to 5 questions in an exam, then
Right.
after solving one question, then uploading it, then only we can go to the next question. So that is creating a problem.
And there is no scanning option in this thing, so we have to upload it as camera photos. And I
Okay.
think there's some problem with people keep getting logging out or something when they try to upload photos. But
Okay.
so it's a very
So
new thing.
I'm sure you guys are smart, way smarter than me. So you will be able to figure it out. So you have to take the responsibility to teach me, how it works. Because if it is made mandatory, I used to work with Google Forms, and I have complete faith with my students that they will not cheat. So, but then if it is mandatory, I have to use that platform only. So some of you have to take the responsibility to teach me as well. Okay, how it works. I'm sure I will be able to pick it up, but not as fast as you, I'm sure. Okay, is that a deal?
Okay, sir. Yes, sir.
Okay. Yeah, because we'll see. We'll see. Do you guys really cheat in the exam? Okay, I'll put this the recording stuff. Okay, then you can answer.